Welcome back, everyone. Wow, it really is powerful. Everyone does quiet down quite quickly. It's actually great to see everyone here. A lot of faces of folks that worked with before, but a bunch of new faces too, which is really exciting. This mission is going to take all of us. There's no doubt in my mind. Well, welcome back for a very exciting afternoon session. It is my job to remind you not to sit in the aisles, not to stand in the back, so please find your seats. We'll take a moment here. I'm going to continue the airplane analogy as well and think, while this may be our last session this afternoon, we're going to continue flying. And we're going to continue flying by having a tanker come up and give us a little extra fuel, maybe. We have a variety of different talks this afternoon. We have everything from lava worlds and yield modelers, credos, astronauts, and servicing, and then Shawn is going to finish it up. So this should be an exciting afternoon session to end our first day. And we will end tightly at 6 o'clock, I promise. Okay, so without further ado, stay on time. Our first speaker is Yamila Miguel from Leiden Observatory in SRON, talking about lava worlds. Let's welcome her, please.
All right. Oh, can you hear me? Yes. Okay. So hello, everyone. It's really a pleasure for me to be here today. I think I'm the first international speaker of the day. So I would like to say that the US is not the only country excited with HWO. Certainly, the Netherlands is very excited about it, but also I think I speak for the whole international community. We all want to see this happening, and it will be a great and amazing mission for all science, right? For the progress of astronomy and science. So today I have the great job of talking about the research we are doing on rocky exoplanets. And in particular, I will focus really on the research that we are doing today, which are the main questions that we are trying to solve and which are the next steps in the field. All right, so at the moment we have more than 1,000 rocky exoplanets discovered. And here I'm also including super Earths that we heard this morning, all the different categories we have for exoplanets from Jesse. And this is really amazing because it's so difficult to find these small worlds, right? But if we want to know if there is life somewhere else in the universe, of course we are not happy only with finding them. We want to characterize them. We want to know which ones have atmospheres, which ones don't have atmospheres, which ones we can remotely say if there is life somewhere else. So we are trying to do our best at the moment to figure out what they are made of, what are their atmospheres made of. And the way that we are doing this at the moment is with indirect techniques, meaning that it's not possible for us right now to observe rocky planets directly. We are observing them together with the light of the star, and we have to correct for that stellar light in order to understand the atmospheres. So Jesse also told you about the transit technique that we are using to try to understand the atmospheres of these planets. But we don't use only the light of the planet when it's passing in front of the star. We also use another technique that is when the planet is passing behind the star, the secondary eclipse. And then what we do is we observe the light of the planet together with the light of the star, and we get really, then we correct for the stellar light, and we get the emission spectrum, let's say, of the day side of the planet. Now, of course, you can imagine that this is very difficult to do for very small planets close to a huge light bulb, as we heard also this morning. But we are doing our best right now to learn about this, to see what we can get. And another thing that we can get from these measurements is the brightness temperature of the planet. And this is very useful. Imagine that you have a huge rock, and you are heating that rock from one side. So if you have a rock, it's very difficult to transport the heat from the day side to the night side, right? So then you will have a very hot side when you are heating it, and a very cold side on the other side. But if you put an atmosphere around that rock, then the atmosphere is much better circulating and transporting that heat. So the temperature that you expect for a planet with an atmosphere compared to the one that doesn't have an atmosphere is different. It's cooler if the planet has an atmosphere. So making these measurements is really helping us to make the first step to try to understand which planets have atmospheres and which ones don't have atmospheres. And this really leads me to the main questions, or some of the main questions that we are trying to answer at the moment when thinking about rocky exoplanets. And the very first one, super basic one, right? Especially if we want to find life somewhere else, but life that we can remotely detect, right? That we can see the atmospheres and see biosignatures. We first need to know which planets have atmospheres and which ones don't have atmospheres. This is a very basic question, and I will go through this during this presentation. But once we figure that out, once we know which planets we have to go and search for atmospheres, next we want to know what are those atmospheres made of. And then after that, once we start in populating our all the rocky planets and trying to understand what these atmospheres are made of, we want to go ahead and try to see which ones of those can actually support life. So these are really the main questions, or some of the main questions in the rocky exoplanet field at the moment. And during this presentation, I will walk you through these questions, starting with the first one. So which planets have atmospheres and which ones don't? And in order to understand this, you have to think that, let's imagine that you have a planet. It has an atmosphere. This atmosphere is made of atoms and molecules, and this planet is also being irradiated, right, from the star. And this irradiation is heating up your molecules very high up, and if this energy that they acquire is very high, then your molecules will actually escape to space. So this is happening to the Earth right now, but of course the rate is very, very low. But if you think about planets that are very close to their stars, or planets that are orbiting very active stars. So this might be a very nasty process that maybe will end up with your planet having no atmosphere after a certain evolution years. So we really need to understand this. And a very useful concept that we are using to try to understand this is the cosmic shoreline. So this is an empirical relation born in the solar system, pretty much thinking like the habitable zone, right? That is a useful concept to try to understand and prioritize targets. I believe that we can think that this is the same. And the idea here is to think of which are, so we have in one of the axes, the accumulated high energy radiation that your planets are receiving. And of course, if they receive much more of that, it's less likely that they will have atmospheres. And then on the other axis, you have the escape velocity. So how much energy you need to put into your molecules for them to escape. If your planet is larger, it will be more difficult for your atmosphere to escape. If your planet is less massive, then it will be easier. So if we put here the planets in the solar system, then you see clearly that Mercury with no atmosphere is on one side, and then Mars with a very thin, tenuous atmosphere, and Venus and the Earth with thicker atmospheres are on the other side of the cosmic shoreline. And you see here like a shaded region because, of course, we don't know how this is mapping up to other stars. So clearly you see on the one hand planets where atmospheres are more likely, and on the other hand, planets where atmospheres are less likely. And this is, of course, our very first order, right, trying to understand this. But now we are trying to see how this maps when we think about rocky exoplanets. So if we take this same plot and we put there some of our best targets of rocky exoplanets to be observed with JWST, this is what we obtain. And I have to say that all these are around M stars. So we heard about M stars this morning. But of course, I hope that in the future with HWO, we can also go to other stars. But right now, these are the best targets that we have. And you see in orange the ones that have been selected by a DDT program of James Webb called Rocky Worlds. That actually the main idea is to try to determine and try to map this cosmic shoreline. And for this, we are getting a lot of time with James Webb to try to determine and map this way better. So then we will know which targets we have to go for. Now, this program is not the only one. We also have other observations with other programs with James Webb. So all the red dots that you see there are rocky exoplanets that have been observed and that have published data. So we have a bunch. You see that most of them are actually in the region of no atmospheres. And we are trying to understand if this is true, right? So we are trying to observe these planets and actually map this and see if this is true or not. And actually, most of them are really consistent with no atmospheres. So this is really showing us and helping us to map this cosmic shoreline. So in this plot, what I'm showing is the temperature of the planets on the day side. Remember that I mentioned before that the temperature is very useful to try to understand or differentiate planets that have atmospheres with bare rocks. And on the other side, we have the temperature of the planets. And you see here the planets that we have observed with JWST. And if the planets are, so this is the temperature divided by what you expect if there is no atmosphere. So if the planets are close to 1, it will mean that they most likely have no atmospheres, that their temperature is more consistent with a bare rock. But if this number is lower, it will mean that you expect to have a more thicker atmosphere redistributing your heat. So this is just a very simplified concept to try to understand this. And you see that most of the rocky exoplanets we have found so far are closer to the bare rock than they are for a thick atmosphere. There is one exception there, LHS 1478b. But that one, actually, there are some problems with the systematic. We are not still sure of the result. That's why it is in gray. But you can see that we are trying to populate this. We are trying to understand our cosmic shoreline to prioritize, to know which are the planets that we have to go and observe if we want to understand atmospheres, and which ones we have to go and observe if we want to understand surfaces. Right. Now, that is for the first question that we are trying to answer. But what about what are the atmospheres made of? And this is really a very difficult question, especially if you think, for example, the planets in our solar system, like Mars, Venus, the Earth, even not planets, but moons like Titan, their atmospheres are completely different one from the other. And this is because these rocky planets have secondary atmospheres, right? Most of them, so here what I'm showing is all the different possibilities for compositions of atmospheres for rocky worlds. But actually, you see the green one there is more close to what we call subneptune, so planets that are much larger, that probably they still have that atmosphere that they accreted from the primordial nebula. But all the others, they have their atmospheres that actually were outgassed from the interior when the planets were cooling down with time. So we need to know the composition of the planets primordially to try to put that in our models, understand how the magma oceans are going to crystallize, and try to figure out what the outgassing is going to be and the composition is going to be. It's really hard. So it's very difficult to predict what will be the composition of a rocky exoplanet. And that's why we need observations, right? To understand this process much better and to understand how it works in general. So all the planets in the solar system are in the blue category, secondary volatile atmospheres. Volatile meaning more water, CO2, nitrogen species. But many of the exoplanets that we are observing right now are actually in the other two categories that I haven't mentioned so far, and that are secondary volatiles plus refractories and rock vapor atmospheres. These are very, very exotic worlds, really things that we don't have in our solar system. So similarly to the super Earths that we heard before, these are things that we just don't have here. It's very difficult to know what these atmospheres are, what these planets look like. So let me tell you a little bit about these lava worlds. Imagine that you have a rocky exoplanet really, really close to the star. And because it's so close to the star, it's always looking at the star with the same face, right? So there is a perpetual day side and a perpetual night side, similarly to what happens with the moon and the Earth. And because of that, one side, like first, let's imagine that there is no atmosphere at all. Just think of your bare rock. So one side will be heated very strongly, and the other side will be completely frozen. And then you will have one side that the temperatures are so high that your surface will be completely molten. You will have a magma ocean on one side of the planet. And we actually don't know what will happen on the other side. It could be completely solid. Definitely, the temperature difference will be huge between one side and the other. Now, the side that is very hot, that has this magma ocean, these magma oceans will vaporize and form a vapor rock atmospheres. Atmospheres very rich in silicate species. Totally alien worlds, right? Nothing that we can even imagine. If these atmospheres are so very thick, then maybe they will circulate to the other side or try to, but as soon as they hit colder temperatures, we don't know what will happen. Maybe it will collapse and there will be some weird cycle being created in these worlds. We have no idea. We have lots of questions and we don't know yet what to expect. But they are very exotic worlds and very interesting also to understand the diversity of rocky exoplanets out there. Now, why it's important to study these planets? Well, here what I'm showing is all the different phases of the evolution of a rocky exoplanet. And if you think of rocky planets, all of them went through a magma phase evolution. All of them. They are differentiated. We know that at some point they had a magma ocean in their interiors. But of course, the ones in our solar system are cold now, are older planets. They are not in that phase anymore. So really trying to understand more about these lava worlds will teach us about evolution of rocky worlds in general, and will help us to fill the gaps about how rocky worlds evolve in general, not only thinking of our solar system planets. These planets are also, if their atmospheres are, outgassed from the interior, so if we observe these atmospheres, they will tell us also about the composition of that magma, and that link between the atmosphere and the interior is very valuable. We can learn a lot about compositions and interiors of rocky exoplanets as well. But even if the planets have already some volatiles, right? If they are so hot, then they will have a magma ocean. And this material that will outgas will enrich your atmospheres as well. So even if you already have a, let's say, CO2 atmosphere, your magma ocean will enrich your atmosphere. So if we observe those species, we will be able to learn more about the interiors of those planets. And finally, and this is really something of right now, it's easier for us to observe planets that are closer to the star, that are hotter, and of course bigger, right? So that's why we are doing such amazing things with giant planets. So these are the first rocky exoplanets that we can characterize. And that's why I think they are also so interesting, because we can learn about the physics and the chemistry that is happening in rocky exoplanets, thinking and observing these worlds. So here is the planetary radius and mass of all the rocky and super-Earths planets that we have, for which we have those measurements. And I'm highlighting one guy there, 55 Cancri E, that it's a very interesting super-Earths. But you also see many other of those red points. The red ones are the lava worlds. So we have many of these planets, right? Many of them. But let me show you the observations that we have for 55 Cancri E. And here, in this case, I'm showing the emission spectrum, so the flux of the planet divided by the flux of the star as a function of wavelengths. And the two dots that you see there is the data that we had before JWST. So you will appreciate more what I'm going to show now. So this is what we obtain now using two instruments of JWST in one of the programs led by Rebollido that is somewhere here in the audience. There was another program as well that was observing only with one of the instruments. But I will tell you a little bit about this, and then I will focus on the other one. So what is it that we can learn from this? So if we plot here what would be the spectrum of a bare rock with no atmosphere at all, or a very thin atmosphere, this is what we would expect to find. So you see that there is a huge difference. Actually, the planet is like 700 Kelvin cooler than what you would expect if it would be a bare rock completely. So I think that a very exciting result here is that we are observing and we are detecting the first atmosphere on a lava world, which is very, very exciting. Now, of course, the next thing is to try to understand what is it made of. And this is more difficult. So first time I saw that dip that you see there at 4.3 microns, I was very excited because I'm a theorist and I was doing models for these planets for a very long time. And in some of our models with CO2 and CO, we saw that dip. So I was like, oh, this is very exciting. But actually it's much more complicated than that. There are many models that fit this data. So the combination of CO and CO2 is definitely one of the models that fits the best the data, and is something that we expect to be outgassed from the interiors of these planets. But there are also other possibilities. And given the diversity of exoplanets that we are seeing, I think that we still need to learn a bit more and to get more observations to have a more definitive answer. But also, besides that, there was another program published by Batel et al., that they observe the planet only, not in MIRI, in the other wavelengths. And basically, they are seeing variability in the different observations. So we know that the planet is variable. We just don't know why. It could be clouds. It could be something in the data. We are learning about this. But the fact that we are asking ourselves and wondering about the variability and potential causes of variabilities in planets that we cannot even see is really, really amazing. So I hope that you get that from this. It's truly amazing that we are wondering, we are asking ourselves, what kind of clouds could these planets have? And it's really cool that we are able to ask these questions. All right, let me go my last minute or so to the very final question, because this is an HWO meeting, and of course we want to know what's coming next, right? So I walk you through the main questions that we are trying to answer at the moment, but of course we are always thinking forward. What is the next question? What do we want to know next? And we want to know, of course, we want to try to observe planets that have biosignatures. And this is very difficult for us to do at the moment. So what is it that we are observing right now? Well, we are observing atmospheres with indirect techniques. We are not observing the planets themselves. So only with HWO, we will be able to directly see rocky exoplanets, which is very, very something that I'm looking forward to. Also, right now, we are studying the hottest planets, definitely not the habitable ones, right? Only if you find some kind of bacteria that can survive in these lava worlds, which I think we will hear more about this on Wednesday. But it's definitely not the most habitable planets that we can think of. So if we really want to go and study habitable planets with atmospheres to try to find potentially biosignatures, then we need really HWO. And that's why I'm so excited about this mission and about all this huge and wonderful community here. All right, I will just finish here, leave you my conclusions, and I hope you have many questions. Thank you.
All right, questions. There's a lot of really cool stuff there. There's got to be a question.
You know, if I'm awake and I'm coming from Europe, you better have lots of questions. Good, yeah. Good.
All right, we got our first question. Please say your name and where you're from, and then the question.
Yeah, hi, my name is Isabel. I'm from the University of Maryland, College Park. This might be kind of a simple question, but I was a little curious about when you said if it didn't have an atmosphere, it would be hotter. How come the rocky planets without the atmosphere don't melt as well?
The entire planet. So we actually don't know, right? So our simple picture now is that they have a magma ocean on one side and it will be solid on the other side. But the interior dynamics is also very complex. And it could be that actually this is also transported to the other side. We just don't know at the moment. There are models that are doing, actually finding different answers, depending, of course, on interior parameters, viscosity, and things like that we just don't know. So it is an open question at the moment.
Any questions online?
Yeah, we have one question online from Michael Best. Given the importance of understanding molten surfaces and tenuous atmospheres on lava worlds, how much of that dynamic can realistically be inferred remotely through spectroscopic and imaging techniques, especially for tidally locked worlds?
Yeah, that is great. This is a great question. So there is actually a program on James Webb that the idea is to observe only the lava worlds and try to understand the dynamics and how they transport the heat and the evolution as well and different compositions. So it's definitely something very, very important as well to observe them, even if we know that they won't have atmospheres. Yeah.
Hard to see up on the top. Yep.
Hi, Akash Gupta from Princeton. So I was curious about your first point here. Like with JWST, we are mapping the cosmic shoreline to know which planets have an atmosphere or not. But I was just curious, how is this concept of cosmic shoreline different from radius valley, which we have also seen how it maps around across planetary and stellar properties?
Oh, that's a good question. So the cosmic shoreline is really a concept that is an empirical concept that comes from solar system, pretty much like the habitable zone. So you just plot in your solar system planets which ones have atmospheres and which ones don't, and naturally you have this cosmic shoreline. The radius valley is something that we are observing in the exoplanet population, and that also involves planets that have thicker atmospheres as well, like super Earth, sub-Neptune-like planets. So it's a slightly different idea, but also the radius valley, we are thinking, is something that we observe statistically in the population, but we don't know the cause. So it could be pretty much atmospheric escape, but there are also studies that say that it could be from planet formation itself. It could be other different forms of escape as well. So it's a slightly different concept, but they are somehow related if you think on the escape mechanism.
I think, let's see, unless there's one more question, one more quick question.
Hi, I'm Edwin Alexani from Rochester Institute of Technology. Great talk, very interesting stuff I didn't know about. I'm curious to know how close the planets typically are to the host star because I'm thinking about the inner working angle for HW. Will we be able to see them?
They are very close. Yeah, very, very close. So they have like more than 2,000 Kelvin of temperature. So, which are the periods? Right now I don't remember. I'll owe you that answer. I'll check it out. But
Great.
Thank you.
Someone has to.
Okay.
A few days?
Yeah.
Yeah, so the inner working angles for M dwarfs are about 0.02, 0.03 AUs. So yeah, I don't think it's possible.
No.
Okay,
We will go to colder and cooler ones with HWO.
All right, well, let's thank Yamila again. Our next speaker is Chris Stark from NASA Goddard. He'll be presenting the Yield Modeler's Credo.
Two 2,500 years. This is how long humanity has been wondering if we're alone. As Jesse Christensen pointed out this morning, in the 5th century BC, Plato and Aristotle were arguing that the Earth was unique. But what you didn't hear is that there was another school of thought at the same time that argued the exact opposite. In the 5th century BC, Democritus was the first person to suggest that there's actually infinitely many worlds, some of which are inhabited and some of which are not. Those same philosophers were asking many other profound questions, like what is the nature of reality? How did we get here? And what is the history of the universe? And in the last 2,500 years, we've come up with partial answers for most of these questions. What is the nature of reality? Well, we've discovered quantum mechanics. We've discovered relativity. How did we get here? We've discovered DNA and discovered biological evolution. And what is the history of the universe? Well, we mostly understand star formation, and we've discovered the cosmic microwave background. But this question has remained, and we have no answer for it. And I'm pointing this out to remind you that Habitable is not out to answer your typical science question. It is arguably attempting to answer the single most profound unanswered question in the history of science and in the history of humankind. So if this is our goal, if our goal is this lofty, we had better get this right. How do we do that? Well, it's going to take three things. So as Bruce McIntosh pointed out this morning, first, we need high contrast imaging to detect Earth-like planets around sun-like stars. Second, as Jada pointed out, we then have to search those planets for signs of habitability and biosignature gases. And the third thing that I'll be focused on is we need a useful sample size. You cannot just survey one star and hope you will get lucky. We have to create our own luck. So how do we do that? Well, here's an analogy. If I were to pull an M&M at random out of this bowl blindly, if I take one M&M, the chances of it being blue are pretty low. But if I increase my sample size and take a whole fistful of M&Ms, the chances that at least one is blue end up being quite high. This is basic binomial statistics, and you can use those statistics to come up with this plot where we are showing what the minimum yield or sample size of potentially Earth-like planets has to be to guarantee that at least one of them has remotely detectable biosignatures as a function of this unknown quantity f sub life, the fraction of them that actually have remotely detectable biosignatures. This plot does not tell you what your yield goal should be, but it allows you to understand the gamble that you are making with the universe. So for example, if we wanted to design a mission that had a 95% chance of success under the assumption that f sub life is 10%, then going up to this line and across, you can see we need to survey about 30 potentially Earth-like planets. This is very important. This allows us to understand how to design a mission around giving us a good chance of success. I would argue what is more important is understanding the implications if we fail to find life. Fortunately, the same plot tells you exactly that. So in other words, if we survey 30 potentially Earth-like planets and none of them show signs of life, then we'll be able to quantitatively constrain that fraction to be less than 10% with 95% confidence. This is tremendously powerful. We have the opportunity to design a proper scientific experiment that will, for the first time in 2,500 years, answer that question quantitatively, regardless of whether the universe cooperates. Now, of course, we have to be able to predict how many potentially Earth-like planets we'll find with HAB-worlds. Fortunately, we have a number of tools to do this. We have several independent pieces of software that estimate this. We call these yield calculators. And we can use these to estimate the number of potentially Earth-like planets that HAB-worlds will find and characterize. All of them take into account a list of astrophysical assumptions, many observational requirements that we impose, and a list of performance parameters of our mission. And then at a very high level, they simulate the survey for these planets. And they all report back a number or a yield of potentially Earth-like planets. That number, unfortunately, is not just a single number. As Dmitry Severansky has been pointing out since 2016, yields are uncertain. So you actually get back a probability distribution of yield that you can expect for a mission. And there are many reasons why it's uncertain. The dominant sources, though, are astrophysical uncertainties. And so I'm showing you here some typical yield distributions for something like HAB-worlds. But I want to give you a caveat. I'll be showing a lot of absolute yields in this talk. None of them are representative of HAB-worlds' final performance. Think of all of these as exploratory yields just to illustrate a point. And what I'm trying to illustrate here is the shape of these two curves. The red curve includes all major sources of astrophysical noise except uncertainty in Eta Earth, how common Earth-sized rocks in the habitable zones of sun-like stars are. The purple curve underneath it shows you what happens when we fold into account the uncertainty in Eta Earth. So you can see why Jesse was so keen on trying to get a better understanding of that number. It is the driving astrophysical uncertainty for this mission and makes this distribution very broad. In spite of that, these distributions are still very powerful because we can pick a yield goal, let's just say 20 for the sake of argument, integrate the fraction of these curves that is larger than 20, and this gives us our best estimate for this mission achieving its yield goal. So for the past year, the project science team has been thinking, how do we move those curves to the right to increase the chances of success for this mission? And we've learned a lot of big picture lessons in the process. And in sort of a tongue-in-cheek fashion, I'm calling these lessons the yield modeler's credo. And I've been trying to hit the project office over the head with these points over and over again. So now I'm going to do the same to you. And if you'd like to be inducted into the very elite Yield Modeling Society, you can raise your right hand and repeat them with me. because right now it's just me and Dimitri here, I think, so we could use some friends. All right, the first point, I acknowledge that trades are not independent. Okay, so some trades work together while others are degenerate. We actually saw this all the way back in 2014. I'm showing you here a table where each row corresponds to a different point in design space. And the column I'm pointing to, labeled phi, is the sensitivity of the yield to one specific parameter. You can see that the sensitivity is all over the place. What that means is the sensitivity of yield to just one parameter depends on your choice of every other parameter. In other words, trades are not independent. And we can take advantage of this in the second point of our credo. I acknowledge that many small changes can compile for the better. Okay, so small improvements to yield can compile like compound interest. Some of them are truly synergistic. We showed this last year where we took the LUVOIR B baseline design, and with just 6 design changes that each on their own were relatively modest, we were able to nearly triple the yields of the mission, move all those curves to the right to scenario F, and decrease exposure times by more than an order of magnitude. So these sorts of trades are out there if we want to invest in them and take advantage of them. Unfortunately, the counter to this point is also true. I acknowledge that many small changes can compile for the worse. I cannot tell you how many times I have run into this. Repeatedly not worrying about small changes in yield will decimate the mission. We all have to pull our weight. And you can see this just from how the yield responds to any individual parameter. Very few of these curves are linear. And what that means is as you degrade any individual parameter, it becomes a slipperier and slippery slope. In fact, if I degrade one of these parameters, all the other curves become even slipperier. So it's even scarier than what it shows on here. Fourth point, for those reasons, I believe a few % change in yield is significant, okay? Not only because of those reasons, but also because a few % change in yield equates to roughly 10% difference in exposure time. And right now at Space Telescope, they're undergoing Herculean efforts to make JWST 1% more efficient. So right now is the time to make this mission efficient. And finally, the last point, I believe that yield is not the only science metric that matters. I can't believe I'm saying that. But it's because yield doesn't fully describe the performance of the mission. We have to worry about things like average exposure times, discovery space, and data quality. And we're tracking all of these things in the project office. So over the past year, we're really embracing these points going forward. And I'd like to show you some of the progress that we've made to date going into EACs 4 and 5. One of the things we've done within the past year is we came up with a list of more than a dozen design changes. And I sent these to the engineers. They ranked them by perceived level of difficulty, or they called it pain. And then we calculated yields going up the scale from left to right, compiling all those changes for both a 6 and an 8 meter inscribed diameter. And again, these are just exploratory numbers. But the point is, you can see for a 6 and 8 meter telescope, you can range from very low yields to extraordinarily high yields. And we have to choose where we're going to operate on this chart. The one thing that we've realized from an effort like this is there's an obvious trade that exists between how many technologies you want to advance and how large your aperture is. So for example, if 49 were the number that we are trying to hit on this chart, you'd have to advance nearly all of the technologies for the 6 meter, whereas for the 8 meter, you'd only have to advance a handful of the difficult ones. Another study we did recently that really pointed to the importance of a large aperture is the yield in the near infrared. So we calculated the yield of the number of exoearths that you could search for carbon dioxide on at 1.6 microns as a function of aperture size, telescope temperature, and detector noise. And you can see going from left to right that at a certain point, once your detector noise is below 10⁻�3, it stops mattering. At that point, you can get a small boost to the yield by cooling the telescope. This is a very technologically challenging thing to do. Alternatively, you can get an enormous boost to the yield by making it 2 meters larger. Aperture size drives yield in the near infrared even stronger than in the visible wavelengths. Why is this? It's because the performance in the near infrared is dominated by 2 things. One is the inner working angle of the instrument, and the other is exozodiacal dust. And aperture size addresses both of those simultaneously. We are ready for EACs 4 and 5 at this point. As Lee mentioned, EACs 1 through 3 were really sort of a sandbox for engineers to play around in. And while they are doing that, the scientists were figuring out what drives scientific productivity about the mission. And now we're bringing those lessons learned together to come up with EACs 4 and 5. This is just a sample of the yield studies that we've run to date. I've highlighted some names here of individuals that will be speaking or presenting posters at this conference on these topics. But I'm very confident that there are a lot of viable paths forward for a mission that, for the first time in 2,500 years, can finally answer this question. Thank you.
All right, thank you, Chris. Questions? We have time for 1 or 2 questions. From the top.
Hi, Aniket Sanghi from Caltech, up here. I was curious, given Ada Earth's importance leading up to HWO, what in your mind is the best opportunity to further constrain that value?
Yeah, great question. So there's actually probably 3 different avenues to pursue to help constrain Ada Earth. Believe it or not, there are some ideas on how to use Hubble to do this. There's the idea that you could reanalyze the Kepler data. I know there's a program to do that. And also, we're thinking about how Roman could help address this problem. Together, all 3 of those, I think we could make a lot of progress. But I'm also of the opinion that this mission does not hinge on that. So I think it's actually possible, in spite of how broad that distribution was, to come up with a strategy where, in the long term, you could have a mission that, in spite of Ada Earth potentially being very low, we could achieve very high yields. Maybe it would require servicing. But those are the sorts of ideas that we're playing around with right now.
All right. Actually, I'm sure there are lots of questions for Chris. I know I already have a couple too after seeing his talk again, but I'd encourage you to find Chris during the breaks and grill him then. Thank you, Chris. Okay, I have the pleasure of introducing John Grunsfeld, a former astronaut, who's here to talk to us about the servicing space opportunities.
Well, I'm very excited to be here. Chris did a great job talking about the 2,500-year history of the question of, are we alone? And what I love about that question is it's actually a well-posed scientific question. And for 2,500 years, people have been thinking, well, what's the answer? And you all are here because you also want the answer in your lifetimes, not in another 2,500 years. And what's so exciting about Habitable Worlds Observatory is we sit here on the precipice where, for the first time in human history, we have the means to launch an observatory that can answer this question and are close to, if not here, with the technology that will allow us to do it. And so I think it's pretty cool to be at that point in human history and just happen to be alive when, in principle, we can answer that question if we can get the proposed yield high enough, and hopefully the universe will be kind to us and we can answer the question. Well, one of the things that is an integral part of the sort of baseline thinking for the Habitable Worlds Observatory is, like Hubble, it will be serviceable. So why service the Habitable Worlds Observatory? And I want this to be part of our language as we go forward. Of course, the Hubble Space Telescope, as you know, President Obama called me the Hubble repairman because I did 3 missions up to the Hubble Space Telescope. The Hubble has been in space for 35 years, 3 months, and 4 days, not that anybody's counting. And the only reason it's had that longevity is because as it was launched from the space shuttle and co-designed with the space shuttle, we were able to go up and service it. And for many areas of astrophysics, the scientific productivity is proportional to the amount of time that your observatory is still alive. And so Hubble has been able to do a lot of science that would otherwise be impossible if it had had a very short lifetime. And so we want Habitable Worlds Observatory to have a long and prosperous lifetime. From a technical point of view, if you were to think about the original instruments on Hubble, and the fact that CMOS imaging detectors didn't even exist, that CCDs were a gleam in engineers' eyes when Hubble was being designed and prepared, the ability to put in second, third, and fourth generation instruments into Hubble is what allows it today to still be a state-of-the-art observatory. But there's some subtleties as well. Servicing, meaning putting in new generation instruments after the launch mission, allows you to make some decisions to get the observatory out to Ursun L2 sooner and then put in the new technology or the latest and greatest technology instruments later that would allow you to get early observations, characterize the performance of the observatory, understand the point spread function, the phase, all of the performance of the observatory, and incorporate those improvements into later instruments. But also by launching the observatory sooner, this is a case where time really is money, we might be able to lower the initial cost of the observatory, in effect paying for those second generation instruments. Now, from a very practical point of view, if you design an observatory that's serviceable, in effect that means that we're going to make it modular and that we can take instruments out, put them back in, take avionics out and put them back in while it's still on the ground during integration and test. And that actually makes it much easier to do that integration and test. James Webb Space Telescope kind of by design, because it was a cooled observatory, was built with instruments that were kind of like one of those wooden puzzles where there's only one way to take it apart and put it back together. That made integration and test very difficult. There's also the possibility that a serviceable observatory allows you to fix things if they break that you didn't anticipate would need to be serviced. Now, again, Hubble is a great example of a serviceable observatory. The International Space Station is serviceable. We did 5 missions up to the Hubble. And what's little known is that in 2004, when the NASA administrator at that time decided we weren't going to go back to Hubble with the space shuttle, we actually started a mission called the Hubble Robotic Servicing Mission. And we were using an arm very much like the Shuttle Canada arm with something called the dexterous manipulator, which is up on station. And we showed that in principle we could change out batteries, the wide field camera 3, and some of the tasks that we eventually did on Servicing Mission 4, we could do that robotically. But we had an artificial time deadline because we believed the batteries were going to fail. And it was determined that the software designed for some of the autonomy and the arm control couldn't be ready in time. And fortunately, that allowed us then to go back with the space shuttle because it was important to service Hubble. Well, space servicing actually has a long timeline. On Skylab, one of the radiators failed to deploy, and the astronauts went out and deployed this big umbrella, as you can see there in 1973. Solar Max mission was serviced in 1984 from the space shuttle with astronauts. Of course, the Hubble servicing missions, we routinely remove avionics and put avionics back in on the outside of the space station using the Canadarm 2 controlled from the ground to keep space station operating. We did a whole series of experiments called robotic refueling mission, showing we can do refueling on orbit using just the robotic arm. And there were some other missions from DARPA, Orbital Express, and now the MRV, which you'll hear about later, which was originally called RSGS, that will hopefully fly next year. So we actually know how to do servicing robotically in space, and that's the idea. Let's make Habitable Worlds Observatory serviceable, but so easy even a robot can do it. That means changing the systems to be modular for the required elements that we'll be servicing. So what might we service? Well, the highest priority would be to take out old scientific instruments and the first generation coronagraph and put in the newest super duper coronagraph that can maybe give us another half an order of magnitude or an order of magnitude in contrast, or throughput, or performance, or wavelength bandwidth. If we want Habitable Worlds to last a long time, out at L2 it needs propellant. If the design doesn't have sufficient margin for, say, 40 or 50 years of propellant, we should be able to put new propellant in. If we're using microthrusters, they have propellant that we might want to replace the whole microthruster module, or if they fail, spacecraft avionics. We always talk about getting higher performance computing on board. So if the computers can be replaceable, or the mass memory units, whatever those components are, to get higher performance. Reaction wheels, anything that rotates eventually wears out. And even perhaps the mirror actuation, because these mirrors are being adjusted once a second. If an actuator fails on James Webb, we potentially can survive a mirror that's malfunctioning. But if we're trying to do high contrast coronography, a mirror that fails in the wrong way could really be fatal. And the actuator electronics, the laser metrology system, the electronics for that could be remote from the actual mirrors, and they could be replaceable. And the teams that have been working on the exploratory analytical concepts have actually been incorporating these features. In fact, in this picture, you can see that their doors, maybe you can or cannot, but the doors are open and you can see the instruments kind of pulled out to give you a concept of the kind of things we've been talking about. So Lee showed these earlier, but we have a couple of general concepts that we've been looking at for how we would service it. What are the servicers? And one would be something like the space shuttle, but perhaps the SpaceX Starship that would approach the vehicle, and robotic arm would deploy, grab, in this case, the EAC-2 concept, berth it into the Starship, and then remove an instrument and replace an instrument. You saw this if you were here this morning. And another concept would be somewhat more conventional, where a visiting spacecraft, a module with a propulsive spacecraft, would grab habitable worlds, again, berth it, and then you can see removing one of the pie-shaped instruments, stowing the old instrument, grabbing a new instrument, and replacing it. And I'll mention that this video that's playing was developed by one of the interns at Goddard Space Flight Center this summer. So I want to thank all the interns that have been working on Habitable Worlds Observatory. Again, so in conclusion, but not really conclusion, because we have a great panel coming up after I speak, serviceability for habitable worlds offers the potential to dramatically increase the scientific return from this observatory, and that's really the highest priority. It may reduce the cost and risk by allowing us to launch earlier and then take some things that might be on the critical path and move them to a subsequent flight. The modularity and flexibility that serviceable Habitable Worlds Observatory offers should make it possible to service the observatory without the need to invest heavily in a servicing infrastructure by using commercial capabilities. And there are many companies that are working on low Earth orbit servicing. We're already doing geo-servicing, and you'll hear about that on the panel, and extending that to the Earth-Moon system as part of Artemis. And so it's not a stretch to think that in the 2040 timeframe, there will be commercial companies that can offer commercial servicing out at Sun L2. And so the project is focusing on serviceability and in the conceptual architectures, and we want to keep that in there until we get to the point where we're an official funded project confirmed, and we can then start working on with the commercial partners on specific space ecosystem that will support servicing. Really the key to being serviced is to keep that serviceability in the design all the way through implementation. So thank you very much, and I think the next is we'll move to our panel.
Yeah. Okay, yeah, so we'll hold on questions for John until we have the panel up. There'll be time for questions within the panel, so I welcome our panel members up. Yeah, grab your water on the way in if you want it. And then I'm going to introduce here our panel chair. Ready, Julie? Julie Van Campen, who's from NASA Goddard, and she'll take it away. Thanks, Julie.
Thank you, everybody. I hope that everyone is excited about servicing after the talks today and then hearing from John. Today we have a great panel, and we'll have an opportunity for some questions from the audience. Also, if there's any questions coming out of John's talk, that would be an opportunity to ask him. We are going to keep our panel session short, and My main goal of the panel is to introduce you to all of these great people who will be here, so that you can connect with them offline, give them your ideas, and find out from them really what the next steps are going to be. As you have already met John, our next contestant on the Servicing is Right is, is Ewan Douglas. He joined the University of Arizona Department of Astronomy and the Stewart Observatory in the spring of 2019. His research focuses on space instrumentation, wavefront sensing and control, and high contrast imaging. All of that sound familiar, right? So he's the lead on as the payload engineer and project scientist for the Deformable Mirror demonstration mission, a CubeSat under construction to test adaptive optics in space using microelectronics. Oh, I'm sorry, we do have. He's the principal investigator with the UA Space Astrophysics Laboratory, which builds high contrast imaging and wavefront sensing and control. Prior to UA, he's come from MIT. He was a researcher for Professor Kerry Cahoy's Space Telecommunications, Astronomy, and Radiation Laboratory. So my question for you is, what does the multiple generations of instruments enable for the coronagraphic instrumentation on habitable worlds?
I think it enables a lot. One thing to remember about coronagraph systems. Oh.
The mic seems to.
Is that better? Okay. So I think it enables a lot. One thing to remember is that coronagraph systems are control systems, right? So you're sensing the light and then you're controlling it. So the sensor improvements, lower noise sensors, can give you a better measurement, and then better controllers, whether it's on the telescope actuation, as John already mentioned, or on the deformable mirror side. You could fly a higher actuator count deformable mirror. And then that could let you also push to different wavelength regimes. You could push into the near UV. We've heard a lot of people mention the ozone sensing in the near UV. We don't have all of those technologies at high TRL yet. So if you could focus on maturing the telescope technologies that would enable the near UV, then it could potentially come in a second generation instrument that would be more capable of characterization without delaying launch.
Thank you. And I also want to mention, you'll hear more about the CSIT, and Ewan is on our CSIT for Habitable Worlds. Next, I'd like to introduce Dr. Kevin France. He's a professor at the University of Colorado. Dr. France's research focuses on exoplanets, their host stars, and development of instrumentation for ultraviolet astrophysics. He's the PI of the Escape Small Explorer concept, NASA's CUTE mission, and a NASA-supported sounding rocket program to develop critical path hardware for future UV optical astrophysics missions. He's currently a member of the Habitable World CSIT and was previously a member of the HST COS instrument team he was also part of the Habitable World START and the LUVOIR STDT, where he served as the study PI for the LUVOIR ultraviolet spectrograph. Kevin, how do you see the work you do in instrument development benefiting the advancement in this field of in-space servicing?
Thanks, Julie. So on the CSIT, one of the things we're doing right now is going through all of the science cases that were submitted by the community and finding not just the most exciting science, but the most exciting science that drives the instrument requirements. And through this process, I think there are two areas that have emerged that make me nervous about our ability to build them soon. And one of them is a desire for very high angular resolution imaging and spectroscopy. So there are science cases that are driving diffraction limited performance down into the far UV. That's very different than what we have on Hubble right now, right, where it's diffraction limited in the optical, but is relatively flat and then begins to degrade as you go into the UV. And the other one is very high sensitivity, high resolution spectroscopy. So I think the possibility of second generation instruments that allow us to get into some of those areas is very attractive. So we've been talking about image correctors or active optics that might be able to take our on-orbit knowledge of the telescope wavefront and be able to correct this without having to build far UV diffraction limited optics right now. It could be a schedule and cost saver. And then looking forward to maybe more, I don't want to say exotic, but next generation detector designs, energy resolving detectors, which may allow us to have both higher quantum efficiency in our detection systems, as well as possibly with energy resolving, remove certain optical elements. So you might be able to get factors of maybe 2 or 3 throughput sensitivity improvement without increasing the mirror size at all. So I think those could be areas where they might not be ready to do in the next 2 or 3 years, but if we knew that we were developing this technology for the future, it could be attractive.
Excellent, thank you. Next, we move into our industry partners. Andrew Allen is the Director of Technology for the strategy for the Robotics and Space Operation Division at MDA Space. He is responsible for road mapping space robotics and sensor technologies across projects and programs. He has over 25 years of experience in manned and unmanned space exploration and is leading multiple disciplinary engineering teams developing flight hardware, payload software, and human factor elements for the Space Shuttle, International Space Station, and now robotics technology for gateway and lunar orbits. Andrew is focused on maturing technologies for commercial robotic satellite servicing as an inventor of patented docking systems and an on-orbit spacecraft refueling system. He has also led the development of a mission-critical targetless rendezvous LiDAR system for human-rated spacecraft and technologies for automatic rendezvous in Mars orbit and safe landing on the Mars surface. That sounds incredibly useful for us, Andrew. What trends have you seen over the last 20 years in the space robotics, and where do you see the industry 20 years from now?
Well, I think if we look back at the shuttle robotics system first, it was originally intended as a payload deployment and retrieval system. So it would be used to, with a skilled, highly trained operator, crew member, to deploy satellites, on the order of as high as 22 tons, and then later possibly retrieve them, maintain them, and upgrade them. And at the time, there was no intention, it was unlikely that extravehicular robotics would be operating at the same time that human operators would be doing EVA. So the shuttle arm became a collaborative robot when the ground designers and operators became confident in the predictability and reliability and safety of that system. And I think that that sort of set the standards for where we need to get to for completely robotic servicing of a large observatory. I think the other thing that we learned in the early systems was that it's really useful to have a general purpose robotic system. And you can do things that you hadn't planned. So very early on, we were seeing that systems and interfaces that hadn't even been designed when the robotic system was designed, commissioned, and first operated, we were starting to use those in orbit. And additionally, we'd have contingency operations like repairing the spacecraft itself or stowing a stuck antenna that we were able to manage because there was a general purpose robotic system on board. Now, as the robotic systems evolved, we became, as John pointed out, much more confident in doing ground control of robotic systems, including dexterous robotic operations, and used things like supervised autonomy on the Orbital Express mission, for example. And now looking forward into the gateway robotics for the Artemis program, much higher levels of autonomy, much higher levels of understanding by the ground crews on how things can be safely and effectively repaired. And all of these are built upon that same fundamental hazard control and safety architectures that human spacecraft operators are comfortable with. So looking forward beyond into the next 20 years, I think we're going to see a lot more reduction in the cost of doing these kinds of repairs, and this will be predicated on commercial organizations building product suites that can be used to produce configured systems that will allow the repair of large observatories like HWO, and also the addition of increased levels of autonomy, supervised autonomy again, where there'd be tenfold improvements in the cost of doing design, verification, and operation of these servicing systems.
Okay, thank you very much. Our next contestant on servicing is Joe Anderson. He is one of the founders and the vice president of Space Logistics, which is a Northrop Grumman company. He has 40 years of engineering business experience in the space industry, with the past 13 years at Space Logistics, helping to make sustainable through in-orbit servicing. Joe also serves as the steering committee for COSMIC, which is a government, industry, and academia consortium funded by NASA to establish and sustain a U.S. leadership in servicing. Joe is also the founder and board member of CONFERS, which is an international industry association focused on promoting on-orbit servicing through policy, regulatory, and technical standards development. Joe, how do you see the advancements across the industry in geospace logistics and servicing providing a foundation for the future of in-space servicing in both Sun-Earth L2 and Moon to Mars cases?
Thank you. Well, first, I want to emphasize the point here that servicing is real today. This isn't something in the future that needs to be developed for HWO. It's something we are doing today. In fact, what you're seeing on the video here on the left-hand side, those are real images. It's not graphics. That is the undocking of our first mission extension vehicle out in geo orbit after it had provided 5 years of life extension to its first customer. There's a second MEV that's currently docked to another satellite. After this satellite undocked, it then drifted across the orbit to the other side of the Earth, and it docked successfully to its next customer, where it's currently doing an inclination pull-down service. So these vehicles are multi-use vehicles. They can dock and undock multiple times. They're docking to satellites that were designed and built in the early 2000s, before anyone thought about servicing those satellites. So these are unprepared satellites that we are able to service today. The figure you see on the right side is one John mentioned earlier. This is our mission robotic vehicle that's being done in partnership with DARPA. Essentially, it is the same as our MEV, only we've taken off our docking mechanisms and we've replaced it with this robotics payload here that was provided to us through the DARPA RSGS program. That satellite will launch next year. It'll have 13 years in geo orbit, providing services of many different types, from installing new capabilities to unprepared satellites to the next generation of satellites that will be prepared to be serviced, where we can install and replace components. So all of these things we're talking about here, about the ability to upgrade satellites over time, they're here, they're now. It's not something we'll be developing just for habitable worlds. So I really want to make that point. And that will apply to all different domains heading out to cislunar into L2. So, I think the point is, we're here now, we can do these things. This work primarily has been commercial. We've got a lot of help from DARPA on this robotics payload we're doing here. There are commercial alternatives available today for these types of things going forward as well. So, it's a very exciting time in space heading into this next generation. And I think there will be a presentation maybe on the last day from John Ehrenberg, my colleague at Northrop Grumman. So please stay tuned and you'll hear much more about that.
Thank you. Last but not least, we have Ben Reed. Ben Reed is the Chief Technology Officer and co-founder of Quantum Space, LLC, a commercial space company dedicated to advancing humanity's journey into the stars, focused on safe, reliable, and efficient space travel further from Earth. Prior to Quantum, Mr. Reed served as the Vice President Engineering for IBX, an innovation and investment firm. In 2018, he served as the Director of Civil Space Policy for the National Space Council, Executive Office of the President. Mr. Reed worked at NASA Goddard Space Flight Center for over 22 years, his final role being the Chief of Exploration and In-Space Services Division. He was lead material engineer for the last 3 Hubble servicing missions. Ben, based on your experience, what are the opportunities provided by a serviceable Habitable Worlds Observatory?
Thank you for that introduction. Thank you for having me on the panel. What gets me excited about the possibility of having a serviceable HWO is that HWO gets funded and built and gets to orbit. Because what servicing brings to the table is the ability to get it, as John mentioned earlier, for less cost, lower development time to the launch pad sooner. Because we don't have to wait for the absolute perfect fill-in-the-blank instrument before we launch. We don't have to wait for as many administration changes as it takes to get a very expensive flagship mission funded to orbit. We can lower the cost by breaking it into smaller chunks, getting it to orbit, and again, as John said, understanding the performance of the observatory so that the second generation and third generation and fourth generation instruments take advantage of or accommodate to the behavior of the observatory once it gets to orbit. Many other benefits that come from having a serviceable observatory. Smaller fuel tank, because it can be refueled, means less slosh. I believe I heard about 37 times today, ultra stable. Well, we want everything there on the spacecraft side to be smaller and tighter, and having serviceable allows that to be the case. Anyway, I could go on and on. I got a page full of notes here, but I'll leave it at that for now.
Thank you. So I think we have a time for a question. Do we have any questions online? Do we have any questions? We have a couple of questions here in the middle.
Yep. Thank you. This question is mostly for John, but if Andrew wants to respond, that would be interesting to me. So you had a slide and you said, so easy a robot can do it. And I just wonder, in your experience repairing Hubble, by the way, I'm a huge fan of your work. Was there any moment or anything in particular that you did that you don't think a robot could do, or yeah?
Well, actually, we're here at the Johns Hopkins University Bloomberg Center and at the Johns Hopkins University Medical School and the Whiting School of Engineering. Some of that work led to the Da Vinci surgical robot. And so now to call that a robot, it's really an extension of a human operating it. But with enough time and money and technology, I think robots can do almost anything that a dexterous human can do. If you have the human brain in the loop, the latency for commanding, just the speed of light out to L2, makes really super delicate stuff more difficult, not impossible. The question is with large language model, machine learning, artificial intelligence, can we get to the point where we can teach a robot to do very fine motor work? And the example is that we repaired the advanced camera for surveys and the Space Telescope imaging spectrograph on the last Hubble mission that involved removing number 4 torque set screws and pulling circuit boards and cutting through EMI grids and things that would be prohibitive to develop the tools and verification that a robot could have done that work in the time frame that we had. Whereas it was something that any good garage mechanic like me could go and do with a little bit of training and help from folks, some of whom are in the audience, and a really good set of tools in a spacesuit wearing hockey gloves. So, well, they were spacewalking gloves, but like hockey gloves. For habitable worlds, I think it's to our benefit to design things that are much more modular, much simpler to do, to increase the chance of success, so that it's something just routine and not something that's so bespoke that it takes a lot of technology and big teams to work out. And thanks for the plug in your talk.
And I'll just chime in there too that John and I talked briefly beforehand about something similar. typically the best thing to do is always keep something as simple as possible and no simpler. But with robotic systems, you can achieve, if you design it correctly, you can achieve sort of superhuman performance in certain areas. But really what you want to do instead is to look at it from a systems design standpoint, and you want to make your serviceable spacecraft robotically compatible so you can keep that simplicity down and try to reduce the degree of autonomy because there's just always risks associated with increasingly complex systems.
Thank you. And do we have a question online?
Yeah, so we have one question/comment from Akibit that says, sounds like a good exploratory use case to potentially leverage currently available and rapidly evolving artificial intelligence capabilities to enhance autonomous operations. Any comments on that? Yeah, any comment on?
Would somebody like to comment on the artificial intelligence portion of it?
Could you maybe just to repeat that question?
Oh, yeah, sorry. So someone, Akib says on Slack, sounds like a good exploratory use case to potentially leverage currently available and rapidly evolving artificial intelligence capabilities, so physical AI, to enhance autonomous operations. So is there any comments on that?
So yeah, AI to enhance autonomous operations.
I think, we're projecting out, 15, 20 years from an emergent technology. But one of the benefits that we'll have with habitable worlds, if you think about training a machine learning system, is that we will have the observatory on the ground, we will be doing integration and test, and hopefully we'll have a commercial robotics servicing partner already lined up before launch such that we can train on the actual observatory and that it can be used, at least in part during integration and test. You may not have an arm that has the capability in a 1G environment to pull out a 3-ton coronagraph, but at least you can be taking data and running those models while you're doing those activities with a crane, for instance. And so when a servicing vehicle goes up to Habitable Worlds Observatory, say 5 or 10 years after launch, it won't be the first time that that's machine learning system, if we're using that kind of autonomy, has seen the observatory.
Well, and John, I would add, you showed the picture of RRM earlier. For that mission, we took a 5 degree of freedom, unbelievably stiff FANUC robot that was used to build cars to simulate the 59-foot, 39-plus Dexter on ISS, extremely floppy, extremely loose, to do those operations that we successfully performed in RRM, stiff on the ground in 1G environment to simulate that environment in orbit. And when you just looked at the video, without knowing the context, you could not tell the difference between the training and the actual operations. So 15 years from now, we will be able to practice on the ground, as John has described, to do the servicing on habitable worlds. You're damn right.
On that note, I invite everybody to take your questions and connect with our panelists here and continue the discussion and the flow of ideas. Join me in thanking them for me.
Okay, thank you. That was a very interesting panel, and as Julie said, we had to keep it short, but I really encourage folks to find them at the breaks and tomorrow and talk to them more about servicing. Our next speaker, I have the pleasure to introduce, is Shawn Domagal-Goldman. He is the acting director of the Astrophysics Division at NASA. You ready, Shawn? Okay.
So yet again, Shawn Domagal-Goldman, Acting Astrophysics Division Director. Really happy to be here today. What a great day. What a wonderful day of talks. Before I get started, I want to thank first our hosts, Johns Hopkins University. This is an amazing auditorium, amazing facility. Let's thank our hosts here at Johns Hopkins. And also, if you're on the organizing committees, the LSC or the SSC, stand up if you're comfortable, raise your hand, just do something so we can also thank you for organizing this week. And it's important that we do that because this is a journey. This is a journey that we've been on for decades, as I'll talk about in a minute. It's a journey that we're going to be on for years to come. And as we go forward, we have to do it really as a community. And that means taking every moment we can to acknowledge the efforts everyone puts into this. And my job here today is to talk about the journey that's gotten us to the point in time where we can build a Habitable Worlds Observatory. And I want you to think about the people in everything I talk about, for the missions, the concepts that have gotten us to the point we're at today. Because every step along the way, there were people that made this happen, that built the great observatories of the past, designed them, operated them, and as I'll talk about, thought of new ways to use them that went beyond their originally intended uses. This goes back to Nancy Grace Roman, often referred to as the mother of Hubble. If we're going to put her in that motherly role, I would claim we should go further than that. Because yes, she did advocate for Hubble. Talk about that in a minute. But she also was the first astrophysics division director. She also helped develop the concept of the decadal survey process that led to the recommendations for every other great observatory that came after Hubble. Chris Stark up here just tapped me on the shoulder and showed me a paper she wrote called Planets of Other Stars. So if we're going to put her in the motherly role, we should claim that she's the mother of space-based astrophysics, and Hubble is just the eldest of her children. And Hubble was the first. We realized, as a community led by Nancy Grace Roman and others, that by putting a telescope in space, it could complement the capabilities of larger optics we could have on the ground. We could see further into the ultraviolet, which we're going to do with Habitable Worlds as well, than we could on the ground. We could get better spatial resolution, as we'll do with Habitable Worlds. And we could see deeper into the cosmos, again, as we'll do with Habitable Worlds. Those were the advantages to getting up above Earth's atmosphere. And I'm originally trained as an atmospheric chemist, so I've got nothing against Earth's atmosphere. You know, one person's signals, another person's noise, but it's important for astronomy that we get up above it. And when we do, we can do things that we can't do from the ground. That's not to say we shouldn't do ground-based astronomy. We need both. They're complementary. You can build larger optics on the ground, and servicing, as much as it's advanced, as we just heard, is easier on the ground today than it is in space. This is ground-based data that I'm showing you. We're going to zoom in on the Andromeda galaxy, and eventually it's going to flip over to Hubble data. I'm going to try to pick off when that happens, but I'm not sure I'll be able to do it right here in real time. You're zooming in on ground-based data. You see the Andromeda galaxy, which gives us the ground-based perspective, which is the context. Right now is where the Hubble data turns on. And you zoom in, and what Hubble gives us is not just finer resolution, not just pretty pictures, but all the stars here. For the first time, we could do stellar populations, not just in our home galaxy, but in another galaxy. Hubble also, according to its namesake, helped us measure the Hubble constant. Its measurements, when combined with ground-based observations, is what led us to invoke dark energy, which then led to something I'll talk about later. And people like yourselves figured out other things to do with this telescope. Planetary astronomy. We have images for planets throughout the solar system. We have UV transit spectroscopy of exoplanets. Exoplanets, aside from Nancy Grace Roman's paper, were largely the realm of sci-fi stuff when Hubble was first conceptualized. And we measure dark matter directly when we combined the measurements of Hubble and the Chandra X-ray Observatory. None of that is stuff that Hubble was designed to do, but we did it anyways, thanks to people. Hi, John. There's John Grunsfeld, who we just heard from servicing Hubble. That's another technology, as we just heard, we're going to carry forward. And you know, this is a theme for when we do great observatories. We develop technologies that will influence the future. In terms of us, what I care about as an astronomer is we can build cool new observatories with it, but we just heard a bunch of our friends from the commercial sector that now have whole businesses spun up to do the things that we started doing with Hubble. On the right, we have the mirror for Hubble, which in addition to being a space-based optic, also taught us how to do UV coatings. And both of these things are going to be important for the Habitable Worlds Observatory. Now, one of the things we did with Hubble is we stared into the blackness of space and we set up a question. We just heard Chris talking about this. We want to ask questions. We design our experiments so that no matter what the result is, we get something profound. When we stared into the blackness of space with Hubble, we said, are there galaxies in the blackest parts of space, or is it empty? It turned out to be teeming with them, which then begged the question, how deep can we go? How far back in time can we look for galaxies, which is one of the motivators for the James Webb Space Telescope. This is what JWST looked like as a concept at a roughly similar point to where we're at today with Hab Worlds, although as I'll talk about later, I think we're more prepared for the Habitable Worlds Observatory than any of its predecessors at an equivalent point in time. This is, of course, what it looks like today. And this is what JWST has seen when we've looked into the blackness of space in the infrared with the larger segmented optics. I know astronomers like to call them little red dots. I'm a pale blue dots guy, so I'm going to go with pale red dots myself. But we haven't just seen these things. We've seen more, brighter galaxies earlier on than we anticipated. And that's still something we don't understand why that's occurring. In my mind, JWST is starting to get fundamental questions about the nature of time itself. As we built JW, just as when we built Hubble, we had to develop technologies to enable it. As it's expanded our literal horizons, it's also expanded our technological capabilities. In this case, we've demonstrated how to build segmented space-based optics. Our model predictions match our ground-based observations on the left, which, except for the little ding we got from the micrometeorite, match the on-orbit performance on the right. We can build these observatories to be scalable to the need at hand, and basically build the biggest telescope we can fit inside the launch vehicle you give us. And as we do so, we inspire people, including my daughter. Just to be clear, she's the one on the right. That's Nancy Grace Roman on the left, Maya Domagal-Goldman on the right. But the other thing I like to point out here is look at JWST itself. There's people looking at that. We opened up our doors so that the public could see the incredible technology that we've achieved as a nation in partnership with our international partners on the mission. This inspires the world. I'll come back to that at the end. I hinted at this earlier, but one of the other things that Hubble set up was this question of what's happening with dark energy. And that's something that the Nancy Grace Roman Space Telescope is designed to answer. On the left is some of the JDEM, the Joint Dark Energy Mission concepts that led to what was called WFIRST, and now is the Nancy Grace Roman Space Telescope. I have to admit, I was a postdoc when this decadal survey came out. I was an exoplanet astronomer, and I wanted TPFI or TPFC or some other exoplanet-focused mission. And so when this dark energy-focused mission was the recommendation, I'll admit I was disappointed. I will also admit that I was wrong. Because as with the other observatories, Roman's going to do things that go far beyond the science case that drove many of its technical tall poles. It's designed to do a lot of dark energy surveys, as I'll talk about in a minute, but it's going to complete our survey of the habitable zone. It's going to bring along with it 200,000 or tens to hundreds of thousands of exoplanet candidates. I don't even think we know how to use that data properly yet because it's such a leap forward in the data volumes we're going to get for the exoplanet community. So I was disappointed, and I was wrong. Because when we build these flagship observatories, they serve the whole astrophysics community because they're generally the best thing we've ever built of its kind. And we'll figure out a creative way to use them for any area of astronomy. Now, what Roman was designed to do was to study the large-scale structure of the universe. Especially, and again, this is an echo of what I said for Hubble, in a way that complements the ground. With better spatial resolution, complementary wavelength range, the ability to see deeper into the cosmos, so that when we pair the ground-based observations with those from Roman, we'll be able to study not just dark energy itself, but how it evolves over cosmic time. And again, no matter what the answer is, it's going to tell us something profound about the universe in which we live. And while it does that, it's also going to develop its own technology that's critical for the Habitable Worlds Observatory. Actually, there's kind of two in one here. The coronagraph is the tech demo instrument. It's going to show us how we can do not just coronography, but high-performance coronography with deformable mirrors. And it's going to be paired with what I would call a stable mirror. With Habitable Worlds, we need an ultra-stable mirror, right? But it's doing these technology developments, and it's doing something else that's very important, which is I could talk to you all day, or anyone, about the lessons that we've learned from our past missions and how to perform programmatically and keep things on schedule and budget. What's better than a lesson learned is a lesson applied. I'll talk about some of the lessons we've learned on how to do on-cost, on-budget, on schedule flagship missions. But what I want you to remember when I talk about that is we're applying those lessons every day on Roman. This picture is 2 weeks ago. In the lower right, you see what I call the exoskeleton for Roman. It's the external structure. It's got the solar panels and a couple other things. And on the top left, you see the guts. You see the telescope, the spacecraft bus, the instruments from JPL and from our industry partners. That part is going into a thermal vacuum test soon. That's the last major test for that part of the observatory. After that's done, we're going to join these two parts of the observatory together, do a couple last tests, and then send it down to Florida, launch it to space, and revolutionize cosmology. That's all we got left to do. Statistically, Roman's 92% complete, and it's undergoing that final environmental testing and integration I just talked about. It's on track for launch readiness by October 2026. That's its current project schedule. Well ahead of the May 2027 commitment, and that's right back to the originally planned date within about a month. And I just want to take a moment to appreciate how amazing that is. This is a multi-billion-dollar observatory. To do a multi-billion-dollar project of any kind, I don't care if it's a stadium or a space telescope, through COVID, through supply chain issues, through inflation, on schedule and on budget, with all those challenges, is an astounding achievement. And it's something we've also learned positive lessons from we're going to carry forward to the Habitable Worlds Observatory. With HabWorlds, we're taking all of those lessons and those technologies and we're putting them together. We want the UV capabilities from Hubble. We want to do it where we can see multiple objects at one time. We're going to take the segmented mirrors from JWST. According to Chris's talk, maybe one a little bit bigger than JWST. We're going to take the high-performance coronography and the stable mirror from Roman and the programmatic performance from Roman and put that all together and you get HWL. Now, we have to advance each of those things. But the point of this is we're not starting from zero. We're not starting from scratch. The technical challenges we have for HabWorlds are built upon the successes we've had on prior flagships and those lessons we've learned from building them. The rest of this decade, a lot of what we're going to be focused on is understanding the concept, as we heard about this morning from Lee Feinberg, trading the different performance factors against the risks that they might entail to the future schedule and cost. We're not going to tell you how much it's going to cost or how long it's going to take yet, because honestly, the uncertainty is large right now. We have to do the homework first before we can give you that answer. And when we give you that answer, not only is it going to be more accurate, well, it'll be more accurate, which also means there's less risk on the back end of it. And by the way, I should point out that these lessons that we've learned, this is not just navel gazing. It does include NASA looking at itself and saying, how can we do projects programmatically better? But the things that we've found when we've studied our own projects matches what the Government Accountability Office has told us, the National Academy of Sciences, and textbooks written on those sports stadiums, highways, and other projects that go beyond NASA. The lessons are the same each time. We're applying them on Roman, and we'll apply them on HabWorlds too. The other advantage we have for HabWorlds, in addition to all of those technologies that we're going to carry forward from those prior flagship missions, is all the concepts. And there's so many people in this room. Actually, raise your hand if you've been on HabEx or LUVOIR or Atlas or HDST, right? Like, okay, round of applause for like half the room, right? I didn't even mention TPFC and the ExoS and ExoC studies. The point is, we've been studying something like Habitable Worlds, not for a few years, not for a few months, but gosh, like 2 decades now. Which means we understand our options well, we understand the technologies we need. I'm not going to belabor this because you've heard a lot about this, although gosh, I wish I could give a whole talk on this. That was a former life. A different path for me would be just giving this talk instead of the one I'm giving. But the point is, and remember I said this earlier, we design our experiments so that no matter what we find, we understand, it'll change our understanding of the cosmos significantly. If we see life, clearly that's going to change our view of ourselves in the cosmos. But if we don't find anything, it's also going to tell us something profound about just how lonely the universe is. We're designing the observatory and the experiment so that no matter what the result is, it's meaningful. And in addition, it's going to do a lot more. It's not, I keep calling it HabWorlds because I'm short on time. It's a Habitable Worlds Observatory, and that last word is important. If you're a grad student, you're a postdoc, if you're online, if you're a high school student, I heard there was an 11-year-old here earlier, the daughter of one of our conference attendees. This is your mission. Every mission we've built so far, astronomers have figured out novel uses that went beyond the original intended design. So I challenge you, students, early career folks, it's your telescope. You're going to be the one operating it. I want you to think of the things that we haven't thought of, the applications for the Habitable Worlds Observatory that haven't been talked about today. Now, to make that happen, we do need, and I said this a few slides ago, we do need to invest early and heavily in our technological tall poles. The good news is we've got a great project team in place that's developed a technology roadmap. And in fact, they've looked at it in such good detail, it's an eye chart. There's a lot of details on here because we know what technologies we need. There's a couple people taking a picture, so I'm going to wait before I go to the next slide. All right. And not only do we know what technologies we need, we have people and teams in place to advance them. And by the way, I keep saying we. I don't mean NASA, right? Like it is a NASA mission. Our sticker goes on the launch vehicle. But when we build these flagships, we don't do it alone. We do it as part of an international partnerships. We do it domestically with our commercial partners. Our estimates for HabWorlds is 75 to 80% of the money that we have for the observatory is going to go out of the doors at NASA to the external community. The we is Earth. Our we alone is not just NASA. We have our industry teams in place already working on previously funded efforts. We have another opportunity that we have a bunch of shovel-ready projects on right now that our commercial partners could advance the technologies in the ways that we need to make HabWorlds achievable, and we can move forward by the end of this decade. In fact, I think we could get to TRL 5 in the next 3 years if we fund those shovel-ready projects. And we've got roses and SAT for SAT and APRA awards. That's the more focused, smaller team awards, both to other smaller institutions, including in the academic community. Taken together, we can get to where we need to be technologically in the next 3 years. These projects are shovel-ready. And if we get those started, something else can happen. For the astronomers know this, but for those that aren't astronomers or in the community, SAT and APRA are two calls where we fund the best technology development efforts. We've been focusing those on the Habitable Worlds Observatory technologies for most of this decade. If we get the Habitable Worlds Observatory technology maturation moving forward, we can use those calls to then invest in the next generation of flagships. Now, we're not ready to do another flagship yet. It's far too early. But the decadal survey did give us something ambitious to strive for, which is a new generation of great observatories, not just the Habitable Worlds Observatory, but also an X-ray and a far IR flagship observatory. We can't do them all at once, but if we want to try to do all of them, we have to do two things. One, we have to do the Habitable Worlds Observatory on schedule and on budget. And two, while we're doing HabWorlds, we have to develop the technologies for the other two so that they're ready to go when their time comes. And once we get the HabWorlds technology moving forward, we're also going to have the capability to invest in these other two missions technologically. And then I just want you to think about two things. One is all the people on all the missions and all the concepts that went into everything I just said. And then the second is what this will mean for the future. People often ask me, or I shouldn't say often, people have asked me, do we really just need to build another telescope if it's just going to give us some pretty pictures? And I would say two things. One, the pictures are really good. But the pretty pictures that you see, as inspiring as they are to the world, that's just icing on the cake after like a 3-course meal of revolutionary science, right? Where we've rewritten the textbooks time and time and time again. This is just dessert. But it's good dessert. And I like to think about the day when the pictures on Times Square and on front pages across the world are of a pale blue dot in another solar system. And I like to think about the generational difference in what that will mean. When I was a kid, one of the reasons I ended up pursuing astrobiology and astronomy is I was out in the yard one day with my little brother, and he asked me, like, we're looking at the stars, we were teenagers, he goes, do you think there's anything out there? And I was like, I don't know. It's a good question. It's kind of what got me on my start. Now, at that time, we didn't know exoplanet statistics. We could have counted the stars in the sky, even in Chicago where there's a lot of light pollution. We could have counted the stars in the sky, but that's about it. Today, if I take my daughter out, or my brother and I take our kids out, we can count not just stars, but planets. Because we know on average how many planets there are per star. If my daughter decides to have kids, or my brother's kids decide to have kids, we can take that generation outside into the yard. And we can count not just stars, not just planets, but planets with biospheres. In fact, we probably will be able to point at a specific star and say, that planet over there has a star around it that has life. And that's how we'll know we're not alone. And this comes back to the beginning of the talk, because we have a legacy to pick up and carry forward. And in some ways, we're not alone, because we're going to do this together. These things take a community that's international, that's both governmental and commercial and academia working together across disciplines. And when you see believe, it means believe in yourself, wherever you are, even the people online, that you've got a role to play in this journey going forward. And that you can help us carry the legacy forward of Nancy Grace Roman and all the other people that touched all those other observatories, sometimes in orbit. And I want to thank everyone that's been a part of this so far. I want to thank all of you today and everyone that's going to be a part of this going forward. I want to take questions, but I think we're out of time. So I'm just going to thank you for yours, and then you can find me. I'll be around all week if you have questions about what I said. Thank you so much.
All right, thank you, Shawn. I think, unfortunately, we are out of time. We have a strict time limit at 6 o'clock here. We're a little bit over. I want to really let's give another round of applause for all of our speakers and panelist members today. Just an incredible day. I hope tonight you get a chance to reflect on everything that we've heard today. I know it's a huge amount of information, but we've got more. We've got 3 days more. We have tomorrow an exciting lineup. We've just heard the start of all the science cases that we'll be able to do with Observatory. We just heard the start of the technology stories, the start of how we're actually conduct this mega project that's coming, and how all of you can continue to be involved. It is going to take all of us, and I really appreciate your time. We'll see you tomorrow. Thank you.